This is a video for our school solar power project. And in this video, the purpose is to try to explain why we get such fluctuations in power production from our solar panels. And one of the big reasons is the sun is not always hitting things at the same angle. Basically, the longer our shadow, the less intense our power absorption will be. When the sun is directly overhead, we get a short shadow and we get a lot of intensity on our panels. It's all hitting a small area, and as our shadows get longer, that energy is spread out over a larger area and we end up with less power from our panels. Okay, and there are a number of things that will affect the angle of sun. One of them is time of day, seasons, and also our latitude. We can't change that much here, but this will help explain why in the summer we get much more production than in the winter. Here's the daily output for March the 30th. You can see it's a nice sunny day and most of the sun is shining down at noon. Here's the next day. It's a little cloudy. You can see some gaps in things. And then here's the output for March. You can see we had some rainy days where, there are days we just didn't get much solar production. And here's our total output. Our panels weren't hooked up till on in October, but you can see that we're on the upswing, and as we head towards June, our output should really ramp up. So to illustrate this, what I've done is I've taken a dollar store flashlight and I've taped a card to the end, and I've cut a little square out so that we can look at areas of illumination and angle, and then we're going to do some math with this. So we have our flashlight apparatus. We also have the two triangles from our math kits that no one ever uses, and these are pretty handy for, if we have straight up and down, and then our angle of inclination at 30 degrees, and then 45 and 60 degrees, and we can use these to set up our flashlight and get an idea of how much area is being illuminated. This activity is taken from Shine On, from the old grade 10 science textbook. So this would probably work best with a partner, but what you can do is, make sure your height from your flashlight is about the same each time, and outline the area of our square when the angle is 0. And then we'll move over and do this for 30 degrees. And you can see it's spread out over a slightly bigger area. It's the same amount of energy, but over a larger area. And then we'll try 45 degrees. You can see we've increased the area again. And then we'll finally do 60 degrees. And with a Sharpie you can see, just what happens to the angle. So this would be, a nice little exercise for calculating areas and looking at ratios. And then we can go back to our data that we get from our solar collectors and just be able to interpret and put some meaning into why we get these fluctuations day to day, from hour to hour, and then over the seasons as well. Here you can see I've outlined the dimensions for the sides, and then I calculated the area in square centimeters for each of our shapes. So let's make some sense of our number here. This is what scientists do. We like to make tables. So let's say we have one flashlight of energy, and originally we used 16 cubic or square centimeters, so we get a 1-to-1 ratio. When we tilted things at 30 degrees, it's still one flashlight worth of energy, but now it's spread over 19 square centimeters, and we end up with 0.84 units per each unit energy. When we tilt again to 45 degrees, it's still the same amount of energy, but instead of being spread over 16 square centimeters, now it's spread over 37 square centimeters, and we get about 0.43, so almost a little less than half. And then finally, when we tilt at 60 degrees, we take that energy that was over 16 square centimeters and we spread it over 81 square centimeters, and we get about 20% of our original amount. So this is why we get much better production from our solar panels when the sun is almost directly overhead. So we'll be expecting better production in June. It's always better around noon when the sun is as high as it can be. And this, I hope this helps make some sense of what we see from our graphs.